slightly different problem than matrix completion, but it makes sense to understand the differences in these problems. So one version of this is called matrix sensing. And in matrix sensing, it's going to sound very similar to sparse recovery. The difference is that the unknown will be, it'll be a vector, but we'll interpret it as a matrix. And so we think of as we're given some linear functions on this unknown matrix. So we think of M as being the unknown planted low rank matrix. And we're given a set of linear constraints from 1 to M, where this unknown matrix has the property that rank of M is at most R, and each Li is a linear function. And so the goal in this version of the problem, matrix sensing, is now to compute argmin over X. So X here is a matrix. We want to minimize the rank of X subject to the constraint that it agrees with our linear observations. So if you were trying to generalize sparse recovery to the matrix setting, this would be your natural first cut approach. After all, here we have arbitrary linear functions of this unknown vector. And here too, we think about our observations as being some known linear function of the entries in some matrix. So we can add and combine them in different ways in some known way, and we end up with these B sub I. So we're thinking about it as taking measurements on some unknown low rank matrix. And we want to be able to recover some structured object, some low rank matrix from these observations. Now, one of the major differences between, this is exactly what you get if you tried to generalize sparse recovery to the matrix setting. This problem really has been studied a lot. Many of the techniques we're going to talk about were first developed for this problem and then were applied to matrix completion. So one of the really important papers in this line is a paper of Recht, Faisal, and Brillo. But one of the major differences is that matrix sensing, these linear functions can often be chosen to be dense. These are settings where you think about some unknown matrix, and what you're allowed to do is you're allowed to sense it with any linear functions that you choose. It's very similar to things like sparse recovery and compressed sensing, where again you think of A as being something which perhaps you get to choose. So in this sense, the natural way that you apply compressed sensing and sparse recovery is in an active setting, where you're really allowed to choose what these measurements are. The same is true for matrix sensing, but there's a big issue when you talk about applying it to the Netflix problem, is because our observations are not dense linear functions of these unknown entries, but are very sparse ones, and they're not ones we get to control. So I don't actually get to tell someone that you should review this particular movie. So I don't actually get to choose which of the entries I observe. Instead, it's something that's purely passive in some sort of stochastic model. And I don't even know what some dense linear combination of these entries would look like, because it'd be like saying to every user, look at every movie and create this linear function of your score and then add them up. So that wouldn't make sense. So it's good to keep in mind that there is this difference between sort of the active version of the problem and the passive version. And what we're really going to be interested in is the passive version of this problem, which is called matrix completion. So let me describe how it's usually formulated.
So, a quick question.
Yep.
So Li is like a active, like not a passive function that acts on M, and that's what we would observe in this different situation? Or what
let me phrase it this way. I mean, in a sense, I haven't described how these LIs are chosen or how they're generated. But matrix completion will be a setting where we think of the L sub i's themselves. You can think of it as a specialization of this problem. But it has the difference that each of the L sub i's we observe are just going to be one sparse. They're only going to observe a single entry. So they won't actually be dense linear functions of this unknown matrix. And moreover, they're things which we're not allowed to control. We're not allowed to choose them randomly, for example. They'll just be passive things that come out of some stochastic model. So let me describe what matrix completion is, and then you'll see what the differences are between these problems. So in matrix completion, we'll be given direct observations of this unknown matrix. So I'll use omega to denote our set of observations. Here, omega is just the set of n cross n, if we think about n as being an n by n matrix. It's just which locations in the matrix we've observed. So this is already one big difference, is that the linear functions here are potentially dense functions of this unknown matrix, and here these are just single observations where we just get to poke into the matrix and see one entry. So again, the rank of m is at most r. And let me let little m denote our set of observations. So we're going to have the same goal. So let me write this and then we can talk about it. Okay, so the difference is that A, we have these one sparse observations. We just get to peer into the matrix and see an actual observation, Mij, an actual entry in it. And one of the other differences that we're going to think about these set of observations is not things we get to choose, but as something which we have passive access to from a stochastic model. So the simplest stochastic model is one where we assume that these observations, we get m of them and they're uniformly distributed. So we just choose m entries completely at random and reveal them from this matrix. So I want to remark that there's something which doesn't quite fit with the version of the Netflix problem. So can anyone think of how this problem is formulated in a way that might give you pause? Yep.
Well, in the Netflix problem, they're not random. They're not like uniformly at random. There's some correlation between how people review movies, and certain movies are more likely to be reviewed than others.
Exactly. That's exactly right. So again, what would this look like? It would look like, there's the assumption of m is low rank. Let's take that for now. Well, what it would look like is, everyone would go home and would choose a random movie on Netflix and watch it and review it. And why would they do that? Just for the common good, so that we have a better understanding of the underlying matrix, right? Do you guys do that? Shame on you.
Saturdays they do that.
How are we supposed to create good recommendations? All right, more seriously though, so just to think about this formulation, one thing I want to tie this into, so does anyone remember semi-random models?
We have like a graph at the bottom and an adversary changes it a little bit.
Right. Anyone remember how the adversary changed it? Come on.
Only in a way that seems like it would help you kind of in
Exactly. Right, so what we talked about in one of these discussion days, we talked about planting a bisection, which is sparser than all the other cuts. So we talked about this stochastic block model, where for simplicity there were just two halves of the graph, which had different connection probabilities inside and outside. Now there are a ton of approaches for then recovering this planted bisection in this random model. What we talked about was a model in which it only seems to make things easier because an adversary was allowed to delete edges crossing the cut and add them inside. So in principle, all it does is make what's the sparsest cut stand out even more, and yet it destroys a lot of the algorithms. So actually the same thing is true here, that we're going to talk about two different approaches for matrix completion. The first of which will be a natural extension of this relaxation, where we're going to write down a semi-definite program, and we're going to prove conditions under which it recovers the true underlying matrix. And then the last thing that we're going to do in this class, we're going to talk about alternating minimization, which is an approach which is really designed in the setting that, this convex program that we're going to prove works is really expensive to try and compute on this big matrix. So what we try and do is we use, things like alternating minimization, which we analyze in the context of dictionary learning and sparse coding. Now the trouble is that the semi-definite program, we can think about a semi-random model. What if we observe m random locations, but then an adversary comes along and reveals more entries in the matrix to us? Sounds like it should make the problem easier, right? The irony is that actually the two approaches we're going to talk about, one being the semi-definite program, that will continue to work in the semi-random model, in much the same way that for the stochastic block model, we had STPs that worked in the semi-random model. But actually, the alternating minimization approach fails when an adversary reveals more entries to you. So that's something which I really think is a benefit to considering different models that come from the theory community is that before you talk about semi-random models, these aren't really talked about in a lot of the machine learning community. You would think that those two approaches that we're going to cover are just as good as each other. In fact, you would think that alternating minimization is better because it's faster. But there's really a big difference between the generality in which they work. One of them actually breaks down when an adversary can reveal more entries to you, which is a very strange thing. All right, so are there any questions about this formulation, about matrix completion? Yeah?
Just really quickly, R, we credit the range is bounded by R. Do we know R? Or is that something, or is it just there?
Okay, so that's a good question. So this is one issue with this model, is that people don't really choose Netflix movies that way. The other thing you're bringing up is also an issue, is that everything I'm going to talk about will be in the exact low rank case. In the algorithm we talk about, we're not going to assume that we know the rank. It'll just pop out. But there's a bigger issue, which is that there's no way that if you fill in this matrix and had every one of these users review every movie, that it would actually be low rank. It would be close to low rank. So in reality, what you actually have to do is the guarantees we talk about for exact matrix completion, you'd have to get versions of those that also work in the noisy setting and give you interesting guarantees. So we won't talk about that because it'll get messy, but that's a very good point, is that those are the versions of the theorem which are much more compelling to actually apply. So are there any other questions about this formulation? Make sense? All right, so our goal roughly is to try and complete M using as few observations as possible. And we're going to need some assumptions to do this. So let me write this up here. And for now, we'll focus on the exact case. So when M really is low rank, we want to recover exactly what the underlying matrix is. As I mentioned, in reality, what you want to do is you want to get versions that still work when M is close to low rank. In that setting, you'd never be able to recover M exactly, but you want to recover something that's close to M. So the sort of two assumptions that we're going to make, one of them is already in the problem. One is just that M is low rank. You hope somehow that if you had the true underlying matrix, that when you take its low rank decomposition or its SVD, that those factors reveal what are the sort of major categories in this, like comedies or drama and so on. Now the other thing that we're going to need is we're going to need something called incoherence. It's a bit different than the version of incoherence that we talked about in the context of sparse recovery. So let me give you an example to sort of motivate it. So let's do the following example. And keep in mind, my goal is to try and exactly recover the underlying low-rank matrix from these few passive observations. Well, let's consider the following matrix. What if we put zeros off the diagonal and R1s on the diagonal? So this certainly is a low-rank matrix. It's going to satisfy condition 1, but not condition 2. And what I claim is that information theoretically, even, you have no hope of recovering what the underlying matrix is with few observations. So can anyone give me some intuition for that? Why can't I recover M from few observations in this model?
With high probability, you're just going to get 0 when you sample something.
Yeah. Yeah, another way to put it is that with high probability, we won't see all the non-zeros until we've observed almost all of the matrix anyways. So as soon as you don't observe some 1, and you don't observe some other 0 along the diagonal, you just have no idea where that extra 1 could go. In fact, I could even delete that 1 and put in a 0 instead and get a lower rank matrix. So the biggest issue is that when we have this passive model and we have that the non-zeros are very concentrated in just a few locations, there's basically no hope of actually recovering the underlying matrix using very few observations. So this is actually something that's very different than the matrix sensing setting. So this is something to keep in mind, is that that example actually wouldn't be an issue if I'm allowed to choose these random linear functions. Because I could do things like I could choose some dense observation, linear combination of the entries in M, and I would at least hit those locations. So this assumption too is actually one of the big differences between matrix completion and matrix sensing, is that matrix completion has this passive and sort of single observation, single entry aspect to it, where you just observe single entries. But the price that you pay is that you need to assume something like not only is M low rank, but its non-zero entries are somewhat diffusely spread out. So that way you're likely to actually see many of the non-zeros. So let me define what incoherence means exactly in our context. So first, let me define the incoherence of a subspace, and then we'll talk about what incoherence means for the matrix now. So let S be a subspace of dimension R. Let PS be the projection onto S. Let EI be the standard basis vectors. Then how we're going to define the incoherence of a subspace, denoted by mu of S, is just n over r, so some scaling, times the max over I of the 2 norms squared of the projection of EI. So this is the technical definition. The way to think about this is that incoherence of a subspace is a way to measure how not aligned you are with the standard basis vectors. So if you think about this, as soon as my subspace contains one of the standard basis vectors, say it contains E1, so it contains the vector 1 and all zeros, then what that means is that when I project that vector onto the subspace S, I get back the original vector, and I would get 1 here for the squared 2 norm. So I'd get n over r. So I'd get a very large value for incoherence, so it's not an incoherent subspace. But if you think about choosing S as a random subspace, then it's actually not hard to see that a random subspace will have its incoherence about polylogarithmic, and that you can find incoherent subspaces which, the incoherence parameter is very small. So in general, the incoherence of a subspace is somewhere between 1 and n over r. And we're going to want that mu of S is close to 1, is not too large, is say polylogarithmic, to get away from some of these issues about having just a few scattered non-zeros. So one way of thinking about this example is that we know exactly what the singular vectors are of this, right? So for example, E1 is a singular vector of this matrix. Because when we multiply, we just get back E1. So that's exactly the problem issue, is that that singular vector only contributes its non-zeros in just one location. So in general, we want that all of our singular vectors contribute their non-zeros in a fairly diffuse way across the entire matrix. And that's exactly what the incoherence of a subspace is getting after. So now let me define the incoherence of a matrix, and then that'll be the technical condition we need. Are there any questions about this definition? We'll say that some matrix M is mu incoherent. I guess I'll call it mu0 just to distinguish it from this mu function. If the following conditions hold. So if we take its singular value decomposition, we want the property that each of its the spaces defined by its singular vectors, its left and right singular vectors, are themselves incoherent. So we want exactly the problem that we want to rule out that issue, because we want that the singular vector is this unknown matrix. They're spread out and they're not aligned with the standard coordinate basis. That's just because our observations are very sparse observations from a matrix M. So we want our observations to be not aligned with the actual, the sparsity of the underlying matrix. And then finally, the last condition we need, these are just technical conditions, is that we need that when we take UV transpose and look at its max entry, we want that that's at most mu0 times root r over n. So these are the technical conditions we're going to need. So are there any questions about this? You won't see immediately why these technical conditions are the right things to do, but we'll see that later as we start to prove things. So now let me tell you the main result, which we're going to work towards proving. There's a ton of work on this particular problem, but this result comes from Candace and Tao. And we're going to show is that say this matrix is n1 by n2, so it's even asymmetric. Then we're going to show is there is an efficient algorithm albeit by solving some SDP that exactly recovers M with this many observations. So let me parse this for you. So we're hoping that we're working with an incoherent matrix. So this is some polylogarithmic term. So that's something that's not too large. The more and more away from incoherence we get, the more observations we need. And that's inevitable for reasons like this, because the non-zeros then could be much more concentrated. We just need more observations to even define what the matrix is. But for matrices whose non-zeros are pretty spread out, so this is some small term, this is some universal constant. Well, if you think about n1 equals n2, then what we're really taking is we're taking r times n times log squared n measurements. Now this is awesome, right? So can anyone tell me why this is great? Information theoretically, how many observations do we need at the bare minimum in order to ever hope to recover n?
Rn.
Yes, exactly. So at the bare minimum, if you think about what a low rank matrix is, when it's rank R, then if you give me its factorization into an n by r times r by n matrix, then it just has 2 times n times r parameters all by itself. So there's no way that you could ever hope to recover a matrix using fewer observations than its number of parameters. So this result is actually telling you that for incoherent matrices, you can lose an extra polylogarithmic factor, and you can achieve this simple information theoretic parameter counting lower bound. You know, that's not even obvious that it's information theoretically true. And moreover, it comes along with an efficient polynomial time algorithm for actual recovery. So this is what we're going to prove. Are there any questions about this statement? You look like you have a question.
I was just trying to think if there are sublinear algorithms for less than n times r. That was, no?
You
I was
just
just
need
thinking
that
about
many
that.
parameters.
But
the other
that don't guarantee exactly. That's what I meant.
Maybe, but they would have kind of weak guarantees. So that we can talk about that later. That's a bit more complicated because you need more assumptions to get that to work. The other thing actually, which is oftentimes not discussed, is see, this is actually, I claim if you get to choose the entries in the matrix, then what you could do is there would always be a way to achieve this. You know, this is really a question about passive and sort of scattered entries, because what you could do is you could observe, for example, just the, you know, let's say the first n of these, you know, the first r of these columns and the first r of these rows are linearly dependent. You could just enforce that you observe all of that column in that row, and then you could fold in and find the rest of the matrix. So this is really a question about this passive observation model. Okay, so there's, you know, a lot of people I should give partial credit to for this. So, you know, some of the first work on this was by Candace and Recht. What they showed was they showed roughly n to the 1.2, you know, r times n to the 1.2 observations suffice. It's a very long and complicated paper. Then Candace and Tao achieved these sorts of bounds. There were simplifications due to Recht based on this idea of quantum golfing that we're going to see next time, which is really the trick for analyzing this approach. It's very similar to what goes on in you know, how you prove correctness for things like semi-random models, where you pass to the dual and use the dual to provide a certificate that the only solution that's optimal for the primal is the one that you're expecting. This is this true underlying matrix. That'll be our pattern for how we prove this. There's been lots of other approaches to the matrix completion problem. So there's a very different approach of Keishon, Montanari, and O. And the last topic that we're going to cover on matrix completion is we're going to talk about analyzing alternating minimization. Of course, there's thousands of papers on this, so this is not an exhaustive list. But what I want to tell you first is the approach. You know, if you remember back to this problem, we had sparse recovery, we had this non-convex optimization problem, where our goal was to find the sparsest linear solution. And what we did was we identified conditions on A, where there's a relaxation that provably works. What I've done so far is we've talked about what are those conditions. We need low rank, and we need this notion of incoherence here for this matrix, which is some condition on its, the space is defined by its singular vectors being diffuse. Well, let me tell you what the relaxation is, because it'll look very similar to what the L1 relaxation is. And this approach was actually introduced in Maryam Faisal's PhD thesis, although there were only empirical results there. So what our relaxation is going to be is we're going to compute the argmin over x, where let me define this quantity in a minute. This is called the nuclear norm. So just like our original non-convex optimization problem looked for the lowest rank matrix that agrees with our observations, here we're going to use some other norm as the complexity measure. We're looking for the lowest complexity solution that agrees with our observations so far. This is an exact case. You can generalize it to work in the noisy case in the natural way. But let me define what this nuclear norm is. This will be, you know, one of the key things that we talk about. Who's heard of the nuclear norm before?
Didn't you teach it at the beginning, maybe? I think. Sounds familiar.
When did I teach it?
Maybe you did.
Sounds familiar,
At the beginning, no?
At the beginning. All right, then you should all know this already. All right, so the nuclear norm which is denoted by this star, is just defined as the sum of the singular values of some matrix. So the way to think about this norm now is it's explicitly replacing L0 with L1, except over the singular values. So we're doing exactly the same thing as what we did with sparse recovery. So to be more precise, let's see why it's exactly the L1 to our L0. Is if we write M as U, and then I'm going to denote it by diag of sigma. So instead of having the capital sigma, which is this diagonal matrix, I'm just going to explicitly write it out as a diagonal matrix of some vector sigma of singular values, and then V transpose. Well, then what I claim is that, well, how can we express the rank of M in terms of this vector sigma?
It's just the L0.
Exactly. It's just the L0. Because it's the number of non-zeros. That's the rank. And what about the nuclear norm? That's just the L1 norm. So this is the same idea again, is that we want to replace this non-convex optimization problem, which is really the L0 of this vector of singular values, with the L1 relaxation, and we want to prove that it works. But proving that it works will be much more involved in this case. So in fact, so that's our relaxation now. It's just compute the minimum nuclear norm solution that agrees with our set of observations so far. And we're going to prove is that this is exactly the result that achieves this theorem. That this convex program really does get exact recovery with this few observations on incoherent low-rank matrices. The other thing, which is kind of obvious, is that this norm is easy to compute. So this convex program really is easy to compute, because if you give me a candidate x, I can just compute its SVD and then add up what its singular values are and get what its nuclear norm is. So there's an issue that comes up, with other sorts of linear inverse problems, that sometimes the natural norm relaxation you want to try actually is not easy to compute, but we won't really get into that in this class. All right, so what I want to do right now is I want to give you a bit more intuition about this nuclear norm and what our plan is for proving that we get exact recovery. So I'm going to outline the plan, and next time we're actually going to see the plan through. But for now, what I want to do is I want to give you other ways of thinking about the nuclear norm. Because after all, that norm is the key to understanding why this convex program works. So we want to think about how we can show that any other solution that's not the true matrix has larger nuclear norm. So first thing I'm going to do is I'm going to give you a dual characterization of the nuclear norm. So let's do that. So for this, we need the matrix inner product, which we might have talked about this already, but between two matrices, which are both of the same dimension, n1 by n2 and n1 by n2, it works even for rectangular ones, but to keep things simple, I'm always going to think about square ones. Well, we're going to define it as just the sum over all ij of xij bij. So all you're doing is you're taking these matrices and you're vectorizing them in the same way. You're flattening them to an n1 times n2 length vector, and you're taking their inner product. Another way that you can think about this is actually, you can take x transpose times b, and you can look at the trace. The sum of the values along the diagonal in this matrix is exactly this quantity. So that's easy to verify as well. It's because, for example, the entry in 1, 1 of this matrix is just the first row of this, so it would be the first column of x, inner product of the first column of b. And that would give us some of the terms here, and we get the rest along the diagonal. Now, the key fact that we're going to use over and over again is we're going to use this fact, that the nuclear norm of x, so it has this definition up here, which is the natural definition, in such a way that you can see that it's the L1 to the L0 we'd like to work with, but is non-convex. Well, it has an alternative description, which is just, it's equivalently the max over all b's, whose operator norm is at most 1, of the inner product between x and b. So this is a dual characterization, because the way to think about this is that any valid b, which has operator norm at most 1, well, its inner product with x gives me a lower bound on the nuclear norm. So first of all, any valid b gives me a lower bound. You should think about this like weak duality. But the fact that there's an equality here is just strong duality, that there always is a b that achieves equality and can all the way get you all the way up to the nuclear norm. So this is just the dual expression of what the norm is. The way to think about this is that the nuclear norm is dual to the operator norm of a matrix. In fact, I think the easiest way to think about this fact is to think about it in an even simpler case. So let's talk about a more basic fact, because you should really think about these two as being related to each other. Let me talk about a more basic fact, which you already know. Or if you don't, we'll prove it. Is if I take a vector now, so this is an Rn, a and take a length n vector and look at its L1 norm, then that's actually the same thing as the max over vectors B, whose infinity norm is at most 1, of the inner product between x and B. So this is a fact which is actually very easy to prove, so let me actually prove it. But you should think about it because, if capital X here is diagonal, if it's the diagonal of some length n vector, S, then its nuclear norm is just the L1 of that vector. And the same way, if B is the diagonal of some, it's a diagonal matrix with this little vector B along the diagonal, then its operator norm is the infinity norm of that vector. So you should already think about this as a generalization of this fact, which is very easy to prove. This fact is actually a little bit more delicate and is not quite so obvious. But fact 2, at least, we can prove. So the proof for fact 2, and this is just the duality between the L1 and L infinity norms in n dimensions. So it's the fact that when you take the geometric dual to, for example, the cross polytope, for those of you who know what that is, you get the hypercube. But the proof of this is just, we proved the two sides of the inequalities. So first, we can look at the absolute value of the inner product between x and b. And this is certainly at most by triangle inequality. Xi times bi. Now, since b has infinity norm at most 1, well, each of the entries is between -1 and 1, so we can upper bound this just by the sum of the x of i's, and that's just the L1 norm of x. So this proves one side of our inequality, that for any valid little b that satisfies this condition, whose infinity norm is at most 1, whatever we get for this quantity really is a lower bound on the L1 norm of x. So that's weak duality. Now we have to say is that there is always a b that achieves equality here. Any guesses for what the b should be that achieves equality for given x?
Bi is equal to 1, like the max norm is 1.
Where's the sign?
The sign. So let's do it this way. So what we can do is we can let bi equal the sign of x of I for all I. And then we have that the inner product between x and b is exactly the sum, I equals 1 to n, of sine of x of I times x of I. And all that is we're correcting the sign so that they're all positive. And we get the L1 of x. So that's a proof for fact 2, right? Is that the L1 norm and the L infinity norm are dual. And you should think about the nuclear norm as the L1 of the singular values, and the operator norm is the L infinity of the singular values. So fact 1 is just the generalization of this to the matrix setting, where it's over singular values instead. So let's prove fact 2, although I'm going to have to punt on one particular issue about it. Are there any questions about that proof? So before we get to fact 1, actually, actually proving it. Let me tell you some of the facts that we're going to need. This is a very useful thing anyways to know. So if we take the trace of A times B times C, and these are all the right dimensions. So this is n1 by n2, this is n2 by n3, and this is n3 by n1, because trace only makes sense on a square matrix, looking at the entries along the diagonal. Then actually it's a basic fact, and it's very easy to check, that this is also equal to trace of BCA. So this is actually a very powerful equality. So sometimes you can even state it without the C, for example. And one thing you can do is you could plug in for A and B, a column vector and a row vector, and you're taking the outer product. And then what you're really saying is that the trace of that outer product is just equal to the inner product between these two vectors. So it's an extremely powerful identity, but there's one huge stumbling block. Is this equal to BAC? No. Might not even make sense, right? So actually this a lot of times makes the top 10 list of most common mistakes by practicing mathematicians. Yeah. No, I mean, it's one of these math overflow types of things. They always have these lists of what are famous bugs in serious math papers, and a lot of times it's this one. So this is probably number 1 or number 2 on the list. So don't do that, because it doesn't even make sense from a dimensionality argument. Don't make the wall of shame. All right, but this is a basic fact that you can check. So the issue is that you can cyclically permute these. And that's actually why I stated it with 3 matrices in here, is because the reason people always make this mistake is because when you have just 2 matrices, all orderings of them work. But as soon as you go to 3, you really do have 1 where the dimensions don't even make sense. So in general, you're allowed to do all cyclic shifts of a product of matrices preserves the trace. This is a fact that we're going to use a bunch of times. So let's now prove at least one direction of fact 1. And then I'm going to talk about how the other direction follows. But that's also a more involved statement. This is something that you can easily check. The other one actually relies on another fact called the von Neumann trace inequality, which is not completely obvious. So what we're going to do is we're going to first show that the analog of this statement, that in this fact that we want to prove, that there's always a B that achieves this value. And this is really important because that's actually the direction that we care about most in proving that that convex program gets exact recovery. Because what we really want is we want a method for designing certificates that any other solution besides our own, the one we're actually expecting, the true matrix, has worse objective value. That's at the end of the day what we want to prove. So we really care about just the inequality on the side, and let's prove that using this fact. Let's prove that there's always a B that actually let's prove the non-interesting direction. Let's prove there's always a B that achieves this. So are there any guesses about how I should, given X, design my B that achieves it? See, here what we did was we had this vector X and we chose the entrywise sign of it. How should I choose my matrix B to actually achieve this equality, given X? Any ideas?
Could I just give it the same singular vectors and choose the singular values to be the sign of the, or that they're all, so all one?
Yes, exactly. Exactly. Let's do that. So that'll be exactly the right dual certificate. This gives you some intuition about how to build up good dual certificates. Well, let's let X equal U sigma V transpose. We know that we want to prove a lower bound, which is the sum of the singular values along this. And the way that we do it is we choose B to be equal to U V transpose. So this is certainly a valid choice in the right-hand side because its operator norm by construction is at most 1. In fact, its singular values are either all 1 or 0, based on whatever the rank of X is. So now what we're going to do is we can just write out that the inner product between X and B, well, this is the same thing as the trace of U sigma V transpose, all transpose, times UV transpose. That's just using the equivalent definition we have of trace of this inner product. It's just the trace of X transpose times B, and we get explicitly this. Now what we're going to do is we expand out what the transpose is. All we get is we get trace of V sigma, because sigma is its own transpose, U transpose, U, V transpose. This quantity right here goes away. One way to think about it is I could just pad this with zeros in here, and then I get exactly the identity down here, and it just completely goes away. Now, how can I get rid of the V? Yes. So all I do is I use this lemma right here, and I move V on the other side, and then I get trace of sigma V transpose V, and this sign goes away, and then lo and behold, I get the L1 of the singular value, so that's exactly the nuclear norm of X. So this is one side, is that there's always a good choice for B, in terms of which certificate is actually going to achieve equality here. So, unfortunately, the other side is actually a bit more involved. So I have to tell you another fact, but it's a good fact to know. So this is actually how you prove this duality between the nuclear norm and the operator norm, is you use what's called the von Neumann trace inequality. And it just says that the trace of let's say, X transpose times B is at most So it's at most the inner product between the singular values. So the way to think about this is, what if X and B were diagonal? Then we know that their singular values are just the entries along the diagonal. And we get, when we take the trace of their, when we take their inner product, is we just get the inner product between their diagonals. And von Neumann's trace inequality just says that this is in general an upper bound, that even though X and B have different singular vectors that diagonalize them, their inner product in this matrix inner product sense is still dominated by the inner product between their singular values. So now we're in great shape, because the other side of this inequality is just that the inner product between X, any X and B, now is just at most the sum of these alpha i's and beta i's. Well, I guess let me call it sigma I here, because that's what we've been using. And these beta i's are at most 1, just by construction, because B has operator norm at most 1. So all of its singular values are at most 1. And then, lo and behold, we get the same bound. So that proves the other side. So are there any questions about this? All right, so let me tell you the plan which we're now going to realize next time. So our goal in the entire proof is what we want to do is we want to hypothesize some other solution, m plus z, is optimal for the convex program. So what we want to show is that this convex program works with high probability, that m certainly agrees with the observations so far, and we want to show that it has the smallest nuclear norm of any solution that agrees with the observations so far. So what we're going to do is we're going to hypothesize that there's some other solution that's better. And we can always write whatever that solution is in this form, because we can think about it as a perturbation of m along some matrix direction z. So can anyone tell me something about the support of z? Remember that we observe m on these locations in omega. So in order for this to even be a valid, feasible solution, something strong has to be true about z.
It has to be supported away from those observations.
Exactly. So you can think about it as, you can only change how you fill in the missing entries, because you have to agree with all of the observations so far. And we hypothesize some other optimal solution, which z, lo and behold, has to be supported in the complement of omega. And what we want to prove is that the nuclear norm is strictly larger than the nuclear norm of m. So this would imply that the true solution is m. It's saying any other hypothesized solution has to have larger complexity. So this actually should remind you of, for example, one of the questions in the P set, where the way that you talk about L1 minimization actually working for sparse recovery is that you hypothesize there's some other solution out there. You look at how that solution differs from the true thing, because it can only differ in the kernel of the observation matrix. And that vector has to add more L1 mass to the zeros than it can possibly subtract. So that's exactly what we want to prove here, is that if we think about z, well, there's a large contribution to the nuclear norm just based on the singular value decomposition of m. Because you can construct a lower bound just based on what its singular values are. So you want to say that no z that's supported in this omega complement can subtract more from the nuclear norm of m in its original SVD space as it has to add on the orthogonal complement to that. So that's how we're going to prove it. And the way to think about this is the way that we're going to prove this inequality is we'll construct some certificate y with the property that y's operator norm is at most 1. And with the property that the inner product between m plus z and y is strictly larger than m star. Sorry. The nuclear norm of m. So one way, just to give you a hint about how we're going to do this, is let's take m, and we can write its singular value decomposition. So we don't know m, but this is very similar to what we did in the context of semi-random models, is that all we want to do is we want to prove that there is a dual certificate that invalidates any other solution. So we're just doing a thought experiment where we can pretend we know what m is. Now what we can do is we can write y as u v transpose plus some extra vector z, some extra matrix z. Now the nice thing is that when we take the inner product between y and n plus z, it's natural to pair up this uv transpose with m and get the nuclear norms contribution. And all we want to do is we want to figure out some way to add to the certificate some z so that we pick up something. Oh, use too many z's. We want to add some x so that we actually pick up some contribution from the cross term that's strictly larger. So can anyone, so this is what I wanted to get at with these facts, is initially when we set x to be 0, when we take this inner product, well, what we're going to get is we're going to get uv transpose with m and uv transpose with z. And the uv transpose with m is going to pick up exactly the nuclear norm. That's the way that we constructed this dual certificate in this fact. And we're going to lose something based on z's contribution in that singular value space. But can anyone think of how can we add some x in a way that we preserve the fact that this is a valid dual certificate and has operator norm at most 1? So what can I do here? So there's some freedom that we're going to exploit. So let me rephrase that. So if I set x to be 0, then I definitely have this condition as met. The operator norm's at most 1, and we're great. Now I want to think about making x non-zero, because that'll be useful in this strategy. And what I want to know is I want to know what are ways that I can set x in a way that I don't affect the fact that the operator norm is at most 1.
Well, by assumption, m is low rank, so we have extra room, basically, to add new singular vectors as long as the associated singular value isn't too large.
Exactly, right? So for example, one thing I could do is I could take any vector, little a, which is perpendicular to u, and b, which is perpendicular to v. And then when I add these in, if they're unit vectors, then lo and behold, I have something which is still operator norm at most 1. So I have all this freedom about how to extend this low rank matrix in the orthogonal complement. And what I really want to do, this is what makes matrix completion so different than the sparse recovery setting, is that the way that I want to construct this x depends on this z. So that's the weird part, right? So you give me this hypothesized, other optimal, better solution, n plus z, and I'm going to look at n plus z, and I can do something like I can project z so that its columns and rows are orthogonal to u and v, and I can use that to actually figure out how to add to x. So I'm going to use my actual knowledge of z to figure out what my dual certificate looks like that proves that your solution is not optimal. So that's the plan that we're going to follow next time. Is the main work will, I'll show you explicitly what x is as a function of z. And the main work will then be showing that this is a valid dual certificate and that we have this strict inequality. That's where we'll use quantum golfing and we'll use some of the stochastic properties of our model. But let me end there. So we'll finish up with matrix completion, at least the nuclear norm analysis, next time. And then we'll talk about alternating minimization for the last regular lecture. Are there any questions about this? No? Clear? Who can finish the proof for me? All right, see you next time.
Anchor, can I ask a question about some other thing?
Yeah.
Under that board?
Yeah.
Or, yeah, could you explain the sign thing again?
Yep.
To me?
So imagine I choose my vector b, so we're in fact 2 7.
Okay, yeah.
I'm going to choose an entry-wise that agrees with the signs of this x vector.
Okay.
And when I take w with this equality,
With that equality,
Yep.
yeah, that's just because you defined b as the
Yeah.
sign. Yeah.
okay,
Yeah.
you agree with this equality?
Oh, yes, it is. Huh.
Agree with this equality?
No, actually, oh, okay, I see. The thing I got confused for a second. Xi is okay. I see. Thank you. My confusion was really dumb. I see.
What was the confusion?
For some reason, in my head, I was thinking x was a matrix. So
Oh, no,
the second
no.
equality didn't make sense because it was
Oh,
like
yeah.
the magnitude of a vector randomly became a number.
So the way to think about this is fact 2 is the specialization of fact 1 to diagonal matrices.
Okay, I see.
And there, all we're looking at is length n vectors because we only care about what's along the diagonal.
So actually, for fact 1, when did you use that the operator norm was less than or equal to 1 when you showed us the proof? Did you use that?
Right here.
Oh, I see.
I use that each beta sub I is at most 1. Otherwise, this inequality wouldn't be true.
I see. Okay. Cool. And what's the difference between operator norm and Frobenius norm? Are they they're the same, right? No?
You tell me.
I think I got confused with all the norms that we have. Because we have nuclear norm,
Yep.
operator norm, and Frobenius norm. Or those are the 3 ones I know.
Yeah,
for
those are
matrices.
just L1, L1, L infinity, and L2 of the set of singular values.
I see. Okay, that's the difference.
Uh-huh.
Yeah. Okay, cool. Thank you, Anchor.
So we're meeting first.